Hi, we're going to take a look at part 1 of vectors. So this is chapter 9 of A-Level Further Maths, the Core Pure book. So a vector is basically any way to represent a line, plane, or basically anything in 3D space. So to know coordinates from 2D, we could use like the coordinate 1, 4, which would be, as you normally see it, 1 square across 4 squares up. We can have the same kind of coordinate in 3D. So let's see what kind of questions they tend to ask at you. So first things first, you're sometimes asked to find an equation going through 2 points. Equation of a line going through 2 points, I should say. In vector maths, all equations are designated with the letter R. And to work out the equation, really straightforward, you can pick any point to start from. So here it's going to be 2, 4, minus 1 as my starting position. And I then want to add on the difference between these two vectors. So I just take them away. If I do 6, 10, 4, take away 2, 4, minus 1, that'll give me the difference between the two. So here 4, 6, 5. And we're then going to add on lambda times that vector. So this here will basically vary. It'll basically take the role of x, so x can be any number, so lambda can be any number. And you can see if lambda is 0, we'll have this coordinate here, or this vector here. And if lambda is 1, we will have this vector here. And again, lambda can be anything, like 2.3, minus 7, 100, and so on and so forth. So this will define a point, this will define a line as you change lambda about. Note, I've said here, find an equation, not the equation, because there are loads of ways you could define this equation. So for example, if you started from 6, 4, 10, you would have a completely different looking equation, even though it would be the exact same thing. Quick bit of notation while I'm here. We have a position vector. That is that vector here. That represents the starting position, hence position vector. The other vector basically tells us how we move or what direction we move in. And that is called the direction vector. Okay, so a lot of questions refer to either a position vector or a direction vector, and that's what they are referring to. Typical question, we have something like this. So we have a vector equation. This is written in a kind of compacted form. I, j, and k's basically stand for like the x, y, and z coordinates. So we could unpack this out into full vector form, which would look like this, where you've got 2i, minus 1j, or minus j, and 5k. They just write it in this form to save a bit of space, because it takes a lot of space to write it in this long form here. Okay, we want to know when this equation crosses the line x equals 0. So if I wanted to cross the line x equals 0, I want to have a 0 here and then work out what the other two things are going to be. So we can basically take this top row off and just deal with it as an equation. So this equation is basically saying that 2 plus lambda or 2 plus 1 lambda is going to equal 0. So now we know that for that to be true, lambda must be minus 2. And now we can just rewrite our equation of our line with lambda being minus 2. So that point is going to be 2 minus 1, 5, minus 2 times 1, 1 minus 2. And working that out, you're going to get 0, minus 3, and 9, unless I made a mistake there. And that will be the coordinate, that will be the point at which this equation crosses the line x equals 0. Okay, and that's an often theme. Often you have to solve some sort of equation for lambda, work out what lambda is, and then always plug it back into our starting vector to give us a point or a coordinate. Okay, other type of really typical question is you are often asked to work out when two lines intersect, when they cross and meet at a point, or asked even do they meet at a point. We can work both of these out. I'll cover both of these now. So for here, notation wise, we have two different letters here because they can change at different rates and both of them can vary. And in fact, we're going to find one solution for lambda 1 and another solution for lambda 2. The best way to work this out is we're going to start off by ignoring this coordinate here. Okay, and then we're going to set both my equations equal to each other. So if I do this, I want my 2x coordinates to equal. So I want this to equal this, and I want my two y coordinates to be equal to each other. So let's write that down. For the x coordinates, we have 3 minus lambda 1 equals minus 2 plus 3 lambda 2. And then for your y coordinate over here, we have 3 lambda 1, and that needs to equal 4 plus 2 lambda 2. And what we've got here is a simultaneous equation. This we can solve fairly easily. Let's just go through it really quickly now. I'm going to take this 3 across and I'm going to triple everything. So let's do that. That will now give me minus 3 lambda 1. If I take this across, this minus 2 becomes a minus 5, which when tripled becomes a minus 15. And 3 lambda 2 becomes 9 lambda 2. We've now got the same amount of lambda 1s with different signs, so we can add them together. If I do this equation plus this equation, I have nothing. 4 take away 15 is minus 11. And here I've got 11 lambda 2. As a quick rule of thumb, they tend to always make these questions have nice answers. If you get a horrible decimal, you totally could be right, but I really would say check it again, because normally you get like a nice number or something and a half. Here we have worked out that lambda 2 must be 1. We can then also work out lambda 1. So let's just take this top equation again, where we had 3 minus lambda 1 equals minus 2 plus 3 now, because we know lambda 2 is 1. And we can solve this. Minus 2 plus 3 is just 1. So 3 take away what gives me 1. That tells me that lambda 1 must be 2. So now I've got a solution. Okay, and this is what you do if you're working out where they meet or even if they don't meet. It's the same method so far. We've worked out that the first two coordinates, x and y, will meet only when lambda 2 is 1 and when lambda 1 is 2. What we're going to do now, we're going to go back to the z coordinate, which I ignored first, and we're going to see if that solution works. If it does work, that means the two lines do meet. If it doesn't work, that means the two lines will never meet. So let's try that. So we've now got minus 1 plus 2 lambda 1, and we're going to see if that equals 1 plus 5 lambda 2. And we have to use these coordinates over here. So it's now minus 1 plus 4, and does that equal 1 plus 5? In this case it doesn't. We have the fact that 3 should equal 6. That is a very, very bad thing, which means that here the lines do not meet. Okay, if these two things were equal, that would say the lines do meet, and then you could also work out what coordinate they meet at. Okay, the next skill to go over is, can we convert from a vector form into a Cartesian equation? So a Cartesian equation just means an equation in terms of x, y, and z. So here we're going to start with a 2D example, so just be in terms of x and y. For 2D or 3D, the method's exactly the same. You are going to basically separate the two equations. So here I have this equation and this equation. You can always basically chop a vector up. And then we're going to rewrite it so that we get lambda equals something. So doing that for the x coordinate, we get that lambda equals x minus 1. Doing that for the y coordinate, we get lambda equals y minus 2 all over 3. Now we've got two equations, both what lambda equals, so therefore we can combine those together to say that that means that x minus 1 must equal y minus 2 over 3. Okay, and now we have an equation that is just in terms of x and y with no lambdas present. I'll do the same example in 3D and it's the exact same idea. So you need to separate x's, y's and z's. So x is 1 plus lambda, y is going to be 2 plus 3 lambda because it is that middle row there, and z is going to be minus 3 minus lambda. And then for each equation I'm going to rewrite it to get lambda equals, and then I'm going to say all those three things are equal to one another. Okay, Okay, so for here, make sure you're okay with rearranging equations. Okay, and then we're pretty much done. All we need to do is, because these all equal lambda, that means they must all equal each other as well. So your overall equation in Cartesian, so in terms of x, y, and z, is this. Okay, notice you've got 3 different parts, and that's how they're always going to look. Okay, this won't always work. So just going for one example where it won't work and why it won't work. It won't work if you've ever got 0 lambda. So for example, if I just look at this bottom thing here, I have that z equals minus 3 plus no lambda. So therefore, to get lambda equals, we hit upon a fairly big problem. So it's impossible to do whenever there's a 0 in your lambda column, in your movement vector or direction vector. Okay, a couple more things to do and to learn. We have the scalar or dot product. It's basically a measure of how long the 2 lines are and how much they point in the same direction. Like, its interpretation is kind of hard to do, but regardless of which, it is really useful. Okay, we have this equation which defines it. So it's a measure of how long the 2 lines are. So these mod symbols, you kind of seen as before, it basically just means distance. To work it out, you would just do 3D Pythagoras. So if you wanted the distance of the vector 2, 2, 1, that would be the square root of 2 squared plus 2 squared plus 1 squared, which would be the square root of 4 plus 4 plus 1 is 9, which is 3. And that tells you the length of this vector is 3. It is 3 units long. And so back onto here, and lastly, cos theta will basically tell us how much they point in the same direction. Because if they point in the perfect same direction, that means theta will be 0. Cos theta is the difference, is the angle between the 2 lines. If you have vector A and vector B, that is the theta that goes into cos theta. Okay, there is a really helpful shortcut to work this out. Okay, I won't explain why, though feel free to look it up. It's not too hard to get your head around. If you want to work out the dot product of 2 vectors, all you need to do is times the 2x coordinates, times the 2y coordinates, times 2z coordinates, and add them all together. So we're going to do 3 times 7 plus minus 1 times 2 plus 4 times minus 3. So times the top pair together, we get 21. Times the middle pair together, we get minus 2. And times the bottom pair together, we get minus 12. That is then 21 minus 14, which should be 7. We can now use that fact and this formula to work out the angle between 2 vectors. So if we dot these 2 vectors, let's call them A and B first. That we can do really easily. That is just going to be here, it's going to be 2 plus 45, or 47. So we've now worked out A dot B. We can also work out the length of A and the length of B by doing 3D Pythagoras. So the length of A will be the square root of 1 squared plus minus 3 squared or 3 squared plus 5 squared. And the length of B will be 2 squared plus nothing squared plus 9 squared. So working these out and leave them in third form, if you've got 1 squared plus 3 squared plus 5 squared, that is going to be root 35. And if you've got 2 squared plus 9 squared, that is going to be root 85. So we've now worked out 3 things. What we need to do now is plug them all into this dot product. So A dot B, that was 47. Mod A was root 35. Mod B was root 85. And cos theta we don't know yet. But now we've got an equation, and the only unknown is cos theta, so we can solve this. So first things first, I'm going to get rid of these 2 terms by dividing by them. That is now going to equal cos theta. And now if I want to work out theta, I just do cos to the minus 1 or arc cos or whatever of this fraction here. Okay, type it all into a calculator and that'll give you an angle. Typically for these I want them in degrees, but do read the question to work out whether they want it in degrees or radians. Okay, key point. This is probably the most important thing, and this is fairly obvious, but it comes up all the time. If two vectors are perpendicular, so perpendicular means they cross each other at right angles, then that means that A dot B must be 0. Okay, the reason is fairly simple. If they cross at right angles, that means that theta is 90 degrees, and you know that cos of 90 is going to equal 0, which then makes the whole dot product must equal 0. Okay, we'll see in a bit when I go through some examples why that becomes so important. Okay, those are the rules in this lesson, as part 1. I'm just going to go through 2 typical exam questions to give you an idea of the kind of thing they're going to end up throwing at you. So here we've got 2 lines with 2 equations. We want to show that these 2 lines do not meet. I actually did this question very similar to one earlier. Just as a recap, you would ignore the third part and you would write up these as 2 equations, and we know we're going to assume that these 2 lines equal each other. So I want the x coordinate from my first line to equal the x coordinate, or the top row, from my second line. And then I'll do the exact same thing with the y coordinates. The y coordinate from the top line, L1, should equal the line from here. Okay. If we solve these together, we can work out what lambda and mu must be. Let's just simplify that. The 2 1s are going to cancel out. And doing this really quickly, mu should be minus 3, which means lambda should be minus 6. Okay. Sorry, mu should be plus 3 and lambda should be plus 6. Okay. And both of those work. And then what we do for the test to show that they do not meet is we would plug those values in z. So for z, we would say minus 1, which is the z coordinate, should equal the z coordinate from this, where we should do 6 plus minus 6, because here this mu, 6 plus minus 3, because here this mu equals 3 over here. These 2 things do not equal each other, which therefore means the 2 lines do not meet. Okay, part B, we want to find out an angle. Again, I counted this earlier. So I'll just do the start. Point A is on line L1, where lambda equals 1. So if we let lambda equals 1, we've then got 1 plus 1, 0 plus 1, and minus 1 plus nothing. We've got point B, where mu equals 2. So from this equation, we've got 1 plus 4, 3 plus 2, and 6 minus 2. These are our 2 points, and it now wants us to find cosine of the acute angle. So you would then use the dot product. You would say that A dot B will equal mod A mod B cos theta. You would then rearrange that to get cos theta equals and work everything out. Work out A dot B, work out mod A, mod B, and then you can work out what the cosine of the angle should be. Okay, I'll go through one more example question. This one is slightly harder, so it takes a wee bit longer because it's a whopping 15 marks. So we have a line given by this equation here. We want to find the coordinates of A where mu equals 1. So if mu equals 1, let's get a thinner pen. That's going to be 8 minus 5, 1 plus 4, and minus 3 plus 3. We've then got a point P with position vector 1, 5, 2. The line L2 passes through P and is parallel to line L1. So parallel means they're in the same direction. So if 2 lines are parallel, that also means they're going to have the same direction vector. And again, the direction vector part was the part that went with the mu or the lambda or whatever letter we want. So write down a vector equation for line L2. So let's call that R2. And it starts with the position vector, 1, 5, 2. And then it's going to have the exact same direction vector. I'm going to change letters because it is parallel. Okay, part C. We want to find the exact value of the distance AP. So the distance between point A and point P. For this, you want a distance between 2 points. All we're going to do is take them away and then do 3D Pythagoras. So if I do a take away P, that'll give me the distance or the difference between A and P. So 3 minus 1 is 2, 5 minus 5 is nothing, and 0 minus 2 is minus 2. We're then going to work out the distance of that, or the length of this vector. So for this length, we have to do 3D Pythagoras again. So it'll be the square root of every single term squared. So 2 squared plus nothing squared plus minus 2 squared. That is the square root of 4 plus 4, so the square root of 8. And I wanted it in this form here, 2 root 2. Okay, so that was 2 root 2, or k equal 2. We are then told the acute angle between AP and L2 is theta. So let's do a quick sketch of what's going on. So I know these are in 3D space, but we can always do a sketch in 2D if we need to. We have two lines. We have L1 and L2. We were told that P was part of L2. A was part of L1. We worked out that this distance was 2 root 2. And now we want to work out the angle between this line A to P and L2. And we are told in the question that this angle here is going to be theta. And we need to work that out. Whenever you want to find an angle, we're going to use the dot product. We're going to use the fact that A dot B is mod A mod B cos theta. Okay? And we need to define a few things. Sorry. So, what we care about for this question is what direction things are going in. We don't care what position they start at. So these A's and B's, they are going to be direction vectors. We already know it for one of them. Let's say B is L2. And we were told ages ago that direction vector was minus 5, 4, 3. So B is the direction vector for L2, which gives us minus 5, 4, 3. We need to work out a direction vector for A. That is just a difference between A and P, which we actually worked out earlier. This here, this 2, 0, minus 2, that is the direction vector for AP, because there's any line or any distance between A and P. So that's how we work out direction vectors. You take two things away. So the vector A can be AP, and that was 2, 0, minus 2. And now we can just plug everything in there. So A dot B, that's going to be the top rows times together, the middle rows times together, and the bottom rows times together, all added up. So minus 5 times 2, plus 4 times nothing, plus 3 times minus 2. That's A dot B. That will then equal mod A. So mod A, we actually worked out before, that is the square root of 2 squared plus 0 squared plus minus 2 squared. That we worked out to be 2 root 2. That needs to be times by mod of B. So the square root of 25, which is minus 5 squared, plus 16, which is 4 squared, plus 9, which is 3 squared, times cos theta. Okay, so all I've done there is I've worked out every part of this equation. Okay, let's clean it up. I'll start over here. I've got minus 10, plus nothing, plus minus 6. So altogether I have minus 16 here. That equals 2 root 2. If you add these together, we are going to get square root of 50. We can write to the simplified third form that you should know is the same as 5 root 2. That's really handy because that means these two terms are going to simplify together in a second. And not forgetting, we have times cos theta here. Okay, let's times those two terms together. So 2 times 5 is 10. Root 2 times root 2 is 2. So that gives me 20 times cos theta. That now means that cos theta is going to be minus 16 over 20, or simplifying down, that's minus 4/5. Okay, let's see what exactly they want. They just want the value of cos theta. Okay, so that's fine. So cos theta equaled minus 4/5. Next, not too much left. We are told the point E lies on L2. So let's update our sketch with a point E. We are told that AP equals PE, so they're the same length. Let me change that then. So point E lies there. And this is the same length, so this is also going to be 2 root 2. Now we want to work out the angle. Oh, sorry, that's not right. AP equals PE, so PE is here. That is 2 root 2. Okay, and that's from there to there. We now want to work out the area of the triangle APE. So we now have this triangle here, whose area we need to work out. This relies to non-right angle trig, and we have the area of a triangle formula that you should remember, which is basically a modified version of a half base times height. This is a half AB sine C. And this is okay, because actually we know all this stuff pretty much. We know this angle because we worked it out just over here, and we know what A and B are. So this area is going to be a half times 2 root 2, which is the length of A, which is one of these two lengths, times the other 2 root 2, which is the other length, times by sine cos to the minus 1 of minus 4/5. Okay, so we've got a tiny bit messy there, but we can still work with it. Let's plug that in and see if that works. We might need to change this in a second, but I'll cross that bridge when we come to it. So let's just type all that straight into our calculator. Okay, so typing that all in, we get an area of 12/5. Okay, and that looks absolutely fine. Okay, now we're asked to find the two possible positions of E. So this question looks kind of impossible at first glance, but the way the maths works of it is we don't really know where point A and point B are in relationship to it. So we could, in theory, have the opposite case, where A was actually somewhere down here, and E was the other side down this line, but still this length remained at 2 root 2. So again, you have to get the idea that these sketches, even though they are really helpful, they are fairly fluid. You can tinker it quite a lot. As a rule of thumb, whenever you want two possible positions, you're either going up the line, say this case, or down the line. That's where your two positions come from. Okay? Let us work them out. So, we have an equation for L2. Let me copy that from up here. That was this equation. We now want to work it out so that we can work out either of these 2 points. We already know we're starting at P, so P is that coordinate. The only thing we're told, the only thing we can use, we know that this has a length of 2 root 2. So that means if you took the direction vector of the whole thing, and if we did 3D Pythagoras on it, it must equal 2 root 2. For this question, lambda's a constant, so lambda you can just take out as a factor. And we actually already know the length of the vector part. The vector part we worked out over here for the dot product, and that had a length of 5 root 2. So lambda times 5 root 2 equals 2 root 2. That means we can now work out lambda. Lambda is going to be 2/5 here. However, that's a problem because we want two solutions, but I've only got one value of lambda. Okay, here we kind of fudge it. So like I said, lambda is going up the line and down the line. All we know is the length of lambda was 2/5. That didn't tell us what sign it was, so lambda can be plus 2/5 or minus 2/5. And now we're finding the position to work out those coordinates. So let's just copy that equation of the line down again. And we can work it out by plugging in those two values of lambda. So we have one option. Do we have names for these two options? No, that's fine. Let me call, so it's called point E. So we can call this E1. I'm going to put a plus in. So plus 2/5 times by this fella here. And then we've got the other coordinate, I'll call that E2. That is going to be the exact same thing, but with a minus 2/5. Let's work out E1 first. So that is going to be 152 plus 2/5 times 5 will be minus 2. 2/5 times 4, that will just be 8/5, and I'll leave that in that form for the time being. I'll change it to a mixed number, so 1 3/5. And 2/5 times 3 is going to be 6/5, which is 1 1/5. We can then just add those together. So it'll be minus 1, 6 3/5 or 6.6, and 3 1/5 or 3.2. Then we do the exact same thing for E2. Because this has a minus 2/5, I want to be taking away here rather than adding. And then again, working them out the same way. So 1 minus minus 2 is 3. 5 take away 1 3/5 is going to be 3 2/5. And 2 take away 1 1/5 is going to be 4/5. And that, with a lot of hard work, is your typical exam question. So again, a lot of parts, but keep in mind right now you only know a few basic skills, so the level's a bit easier. It will get harder because all you can really do is take a dot product and do basic equations of a line, so you don't have too many skills to worry about right now. Okay, again, looking for keywords to give you hints. Again, whenever an angle is involved, you're going to have to do a dot product. Okay, again, parallel lines mean the same direction vectors. There are a few hints in the questions that if you look for them, will make it really handy. Okay, thanks for listening, and I hope that was helpful.